Quake's 100-meter map was created in the early 2000s by Attila Cerniak and is the perfect testing ground for raw speedrunning skills. Over the years, the world record on this map has been broken many times as techniques improve. Here's the current human world record. Over the past few months, I've been writing a bot that attempts to beat this run. In my previous video, I used reinforcement learning to do this, which beat the world record run by a single frame. This time I've taken the approach of reverse engineering the human record shown here and improving it using optimization techniques. As before, the goal will be to keep the inputs somewhat human-like, so impossibly fast mouse movements or rapid key pressing are banned. The hope is that any new techniques I discover can be used by skilled human speedrunners to improve on the world record. In order to reverse engineer the world record, I worked with what's known as a demo file. In 1996, it wasn't possible to simply record a gameplay video, so in order to share footage, Quake has the functionality to create a compact demo file which can be watched back on other machines with Quake installed. The idea is to extract the player's inputs from this file and use these as a basis for a new bot. Quake's demo file format is strongly linked to the game's networking code. Being a multiplayer game, Quake is split into client and server components. When playing over a LAN or the internet, the client and server run on separate machines, and messages are sent and received over the network. The demo file is just a recording of the messages sent from the server to the client, left to right in this case, along with the current view angle of the player. When playing locally, the situation is exactly the same, it just happens that the client and server components run on the same machine. Here is a representation of a demo file in human-readable form. The file starts with commands to define the initial state of the world, for example telling the client which map to load, which models to load, and the initial positions of entities within a level. This section isn't really important for our purposes, so we'll skip over it. After the preamble, there is a sequence of messages for each physics frame processed. For a speedrun on the 100-meter map, there are just 3 messages sent per frame. The time message simply gives the game time in seconds. The other 2 messages give information about the player. The update message gives generic information about the player, enough to be able to draw the player in the third person. Were there other players in game, then they would each also have their own update message. The client data message, on the other hand, contains only information relevant to the first person view. Even with multiple players, only one of these messages is ever sent per frame, and it only contains information pertaining to the player that recorded the demo. As well as the server messages, the demo file also contains a 3D angle. This is the client's view angle, and since it's not sent back from the server, it is necessary to record it in the demo so that the client angle is known when playing back the demo. This sequence of messages repeats for the rest of the demo, with 72 updates per second. The demo file does not include the keyboard inputs directly, but it does include the player's position and velocity. However, it turns out that this is enough to recover the inputs. To see how, we must first learn a little about the Quake physics engine. As we saw earlier, Quake operates on a frame-based system, with 72 physics frames being processed per second. On a given frame, the current physics state is acted upon by the player's inputs, key presses and mouse movements, in order to generate the state for the next frame. In code, the relevant physics state can be represented like this. It's just the player's velocity and position, along with a couple of flags. Let's ignore the flags for now, since they're not important for this discussion. The inputs are also quite simple. Just 5 Boolean values corresponding with the arrow and jump keys, and 2 scalars which give the view angle, which is derived from the mouse position. Finally, the apply inputs function represents Quake's player physics code, which takes the state and player inputs for a given frame and returns the state for the next frame. I've implemented this code in a Python module which includes logic for collisions with the floor, player acceleration maths, and input handling. As such, it can perfectly simulate the Quake physics code of a simple flat level like the 100-meter level. Having a programmatic interface means I can use it to trial new bots and to aid in the reverse engineering process. In theory then, since the demo contains the position and velocity, we can recover the state objects completely. As the demo also includes the view angle, This means that the only unknowns are the keys pressed on each frame. For any frame, we can simply try all possible key combinations and see which yields the following frame when passed through apply inputs. With 5 possible keys, this comes out to only 32 possible key combinations to try, which would be easily doable. However, there is a problem with this plan. The velocity and position are quantized severely in order to save bandwidth, so much so that this brute force approach would not work. Instead of working frame by frame, we can try and find an exact initial state along with keyboard inputs for each frame that is consistent with the rounded states seen in the demo. Here's an illustration of this idea with 2-dimensional states rather than 6-dimensional. Each box shows the state that would be permitted for the rounded states observed in the demo file. The goal is to get each origin, denoted by the white crosses, into the corresponding box. When this occurs, we say the frame matches the demo file, which is shown here by colouring the box green. We have free control over the initial frame's location, so to match the demo file, we just need to pick a location within the box. To change the location of subsequent frames, we change the inputs preceding that frame, and so we search the space of initial locations and keyboard inputs until all frames match the demo file. Let's write out some pseudo-Python to map this idea into our full problem. Given a candidate initial state and set of keys to press for each frame, this code evaluates the resulting state trajectory and returns how many of these states, when quantized, match the demo. The trajectory is evaluated by repeatedly applying our apply inputs function. Each frame is compared to the demo data by a function called state matches demo frame, which works by quantizing the state and seeing if it matches the already quantized demo data. Finally, the total number of matching frames is counted and returned. All that then remains to do is to maximize matches demo with respect to its arguments. If we're successful, we will find a set of inputs that match all of the frames. The problem of optimizing, that is maximizing or minimizing an objective function with respect to its arguments, is a massive field in computer science. Decades of research has been done into this area and many practical algorithms have been discovered. To illustrate the idea of optimization, here is a representation of a 2D function. The function takes coordinates in the horizontal plane and returns the height of the corresponding point above that plane. The goal here is to find the coordinates of the highest point in this surface, which is known as the global optimum. For this problem, I've used an algorithm known as differential evolution, a genetic algorithm. The details are outside the scope of this video, but in short, the algorithm maintains a population of potential solutions. At each step, one of the members of the population is translated according to the difference between two other members of the population. If this yields a point higher up on the surface, then the updated element is kept, otherwise it reverts to its previous value. This continues until the highest point found stops increasing. There are a few more bells and whistles to the actual algorithm, but this is the gist of how it works. I've shown differential evolution working on a toy problem with 2D inputs, but it can be applied to any function that takes a fixed length input. To get it to work with matches demo then, we just need to come up with a vector encoding of the function inputs. Practically, this involves writing a decoding function and plugging this decoder into matches demo in the objective function. The optimal inputs can then be recovered by decoding the vector returned by the differential evolution routine. Finally, the algorithm requires upper and lower bounds for each element of the vector, which are used to constrain the population. Once I'd come up with a suitable decoding function, I was able to reproduce the results for almost all of the world record run. Here's an illustration of these inputs. At the start, the player looks sharply to the left and then sweeps the mouse to the right while holding forwards and right. The player then taps the jump key. Once in the air, the player holds left while turning the mouse left. At the peak of the jump, the direction is reversed. Finally, as the player reaches the ground, the forward key is pressed and jump is pressed again and the process repeats. Those familiar with Quake speedrunning will recognize the above inputs as power bunny hopping, a form of strafe-jumping. Despite the serpentine path, these inputs propel the player forwards faster than any other known method. I won't go into the details of why it is so effective, but it is similar to Quake 3's physics, which I've covered in a previous video. The final part of this project is to write a bot that can improve on these results. I wrote an agent that roughly follows the same inputs as the world record, an initial turn left, slow turn right while holding right, etc. However, I added free parameters to adjust things like how long to hold each key or how fast to move the mouse at various points. Here's an illustration of a few of these parameters and how they affect the path of the player. The markers on the line indicate the time in seconds when the player reaches the labelled point. The goal then is to find a set of parameters such that the time when the path crosses the finish line is minimized. This is another optimization problem. We want to select bot parameters that minimize the finish time, and once again it can be solved with differential evolution. Here's the progress of the solver as it proceeds through candidate solutions. Here's the optimized bot playing on a Quake server. Let's see how it compares to the human world record. This shows that following the current world record strategy with frame-perfect inputs, there is still at least 0.15 seconds to be gained. But the more interesting thing that this system provides is a framework for trialling new strategies and seeing how they compare in a like-for-like setting. I tried a few different ideas, with one in particular standing out. Instead of changing direction twice per jump, why not change direction 3 times? This way we'd travel a straighter path and thus reduce the total distance travelled. At least that is how the theory goes. Let's see how it does in reality. I modified my bot to perform 3 turns and re-optimized the parameters, and here is the result. As you can see, this provides a decent improvement. I also reckon that it's reasonable that a skilled player will be able to execute such a 3-turn jump as well as they can execute a 2-turn jump. As a result, this looks like a promising avenue for improving the human world record time. Furthermore, the same theory should apply beyond the 100-meter run, at any other point that moving in a straight line is required. In terms of what to try next, the optimization techniques explored here should work well on other Quake maps. To do this, we'd need an apply inputs function that takes into account the more complex geometry on these maps, which would be most easily done by integrating with the Quake code directly. Generalizing the demo reverse engineering technique could prove challenging, since it would require solving for the positions and velocities of monsters and moving platforms. However, the technique should work fine for segments that do not interact with other entities. I hope you found this video enjoyable. If you did, please click like and consider subscribing. As always, please leave a comment if you have any questions.